Welcome back to our next lecture in engineering mechanics, EGM 3512, in which today we will focus on the center of gravity and centroids. And if you never dealt with these before, that's exactly what the lecture is about. I will introduce them to you from a scientific standpoint or from an engineering mechanics standpoint. So let's take a look at our actual objectives here today. So first, I want to actually define and introduce the center of gravity for 3D objects. And no worries, we will very seldomly deal with 3D objects in this class when it comes to the center of gravity, but it's always good to start from that high level and then work our way down to 2D systems, as we will see later. However, before we go down to 2D systems, we actually want to be able to differentiate between the center of gravity, the center of mass, and the centroid. So these are often used interchangeably, but they have a specific definition. And they also have, as you will see, very much the same kind of formulas to calculate them, but they are different in a certain sense. And our goal is to actually differentiate those clearly. Once we've done that, we will actually reduce our analysis to look at only 2D systems, because you will see those most often. And as you will see in the homework that I will look at with you in just a second here, you will mostly deal with two-dimensional systems here. Then we will calculate, of course, the centroid location for a specific defined area, and we will define that through a function that looks scary first, but hopefully I will be able to decipher that for you. And then our ultimate goal is to actually determine support reactions of a simply supported plate with a random shape. And the random shape here actually then goes back to the function f of x, and that's why we first talk about that. Now, before I go into the lecture this time, let's actually take a look at the homework so you know what's ahead of you and where we're going with this. So I think instead of talking about each of these problems, this is a warm-up problem, this is a warm-up problem, it comes down to these two problems here. And let me use the one here on the top, problem C, as an introduction of where we're going with all this. So what you see here is a plate that has an edge length of 3 feet and 3 feet on the bottom. And then we have a random edge here. And that random edge is defined by a function, x squared over 3. And right now we don't care about the function, but what I need you to understand is that this entire plate here has a support reaction at A and one at B. And it wants to, of course, fall down under gravity. And how does it want to do that? There's actually what's called the centroid in a geometric sense, or the center of gravity in a physical sense. And I pretend for a second that's right here in the plate. That's obviously not correct. It's not to scale, but you probably will understand that gravity wants to take the entire weight of the plate and push it down in this direction, or pull it down in that direction. And so once you would know what the force of the plate is, so I'm going to call that force plate, and you were to know the distance that the centroid location, or the center of gravity in this case, has to the y-axis, right? Let's call this here x bar for now. Then I could actually calculate all my support reactions. And not that you need to fully understand this right now, but where we're going is we obviously have a tensile force here, and therefore we must have a support reaction here that goes in this direction. And we also must have a support reaction that goes up here. And I can already tell you that this upwards is of course equal to the total weight of the plate, because the only thing that goes down is the plate, and this is going up. But again, this is not about numerical values here. This is only about the concept. So this would be equal to that. And now you probably understand that if I take the sum of the moments about point A, the two things that have a lever arm would be what I call RBX. And also F plate. And so to calculate RBY, I would just set up an equation that says the sum of the moments about point A is equal to 0, and 0 is equal to RBX multiplied by 3 feet. That's the lever arm, and that actually happens to rotate counterclockwise, so therefore I'm going to make that positive. And now I have my F plate, and maybe I use red for that, F plate multiplied by what I called X bar. And that rotates clockwise, therefore that is negative. And now you can solve technically for RBY, right? So you could solve for this value. And what you need to know, or the one thing that you at this point in the class do not know yet, is actually what is the weight of the plate, although you probably could calculate that yourself if you know the area. But what's brand new here is how do you get this value? So this is really the focus of today's lecture. How do I get X bar? And that is the distance between the centroid of the plate, right? So I'm going to call that here C for centroid of the plate, to the origin, right? So the origin is down here, O. And that is really the goal of today's lecture, to understand how can we calculate the X bar. And then as a bonus, we also will talk about how to calculate the weight of the plate, although you probably know this technically from classes you have taken before. Why? Because ultimately our goal is to find support reactions for systems like the one shown here. So that is the introduction to why we're doing what we're doing. So now let us move on, and let's first talk from a very high level. In fact, let's talk from a 3D standpoint. So let's talk about the center of gravity first. So center of gravity. And first we have to make a few observations. Before I make these observations, let me introduce you to what's called the mechanics potato here. So this potato is a random shape that is floating in random space, and it is not very much defined except for a few things that I will call out for you in a second. But notice that we have also a randomly oriented coordinate system, an origin here, and that behaves random to this potato. However, later on you pick that, of course, in a very smart way. But right now our goal is to generalize it. So the first observation that I have to make about this potato, it's pretty much any physical body. So any body is composed of multiple components. And these components here, I call them dW. W for weight and D for super tiny, super small. Right? And because it's super tiny, super small, there's infinite amount of them. So my first observation here is that any physical body is composed of an infinite amount or an infinite number of tiny particles, right? Of tiny particles. And those tiny particles, in mathematical sense, they are of differential size. So differential size again stands for dW. So dW stands for tiny, and W stands for weight in this case, because we're talking about the center of gravity. So that's our first observation. The next observation comes also from this picture here, and we see that this dW, which of course exists many, many times, but dW has a distance to the origin of the coordinate system. And this distance is not randomly named like this. It is actually called x tilde, y tilde, and z tilde in the respective coordinate direction. But please note that it's a tilde. So the dw has a specific distance, which is x tilde, y tilde, and z tilde. While this coordinate origin is randomly chosen and the potato is randomly in space here, we can say that any random particle has these three distances. So each particle has a distance to the origin is my next observation. So each or all, each particle dw has a specific distance to the coordinate origin. And that we call x tilde, y tilde, and z tilde. So far, only observations here. One last thing, of course, I just want to emphasize again, is that each particle also has weight, right? So it's not weightless, it has weight, it's just super tiny in this case. And now we can pretty much complete our fill in the blank here on the bottom. So x tilde is the distance between the particle and the coordinate origin in the x direction. So distance between particle, and that's the super tiny particle, so dw, distance between particle and coordinate origin. And in this case, it's in the x direction. In the x direction. And of course, I have the same for the other directions. So I have here for in y direction. And I have in z direction. So just to be clear, here I have my z direction. Then here I have my y direction. And here I have my x direction. And again, the term you want to memorize is the tilde, right? Or the symbol you want to memorize is the tilde. And let's talk about the distance for one more second here. So it's not the distance to anywhere actually of dw. So dw technically has a centroid too, but it's so tiny we don't really care about it. So we just consider dw like an infinitely small point, and therefore it just goes from that point to the coordinate origin. And with that said, we now have the observation of dw, and we can move on to further observe the potato. So let's go to the next page. And here I see the very same potato, but with a little bit different representation. So let's make some observations first. Again, the potato is given here in the random coordinate system, but notice that now I'm not dealing with dw anymore. What's shown here is w, which is the total weight of the potato that passes through a point called G, and that is the center of gravity. So let's write that down. Center of gravity. And another observation that I can make now is that the center of gravity now is not given with x tilde, y tilde, and z tilde anymore, but it's given with x bar. So x bar, y bar, and z bar. And that is not random here. So that defines the distance from the coordinate origin to the point G. So two things I observe in this picture. I have the total weight, right? So we'll write down an observation there, and that is the resultant force of the particle system. So the resultant force of the particle system is the total weight of the potato, is the total weight. But a mathematician would never say it that way. A mathematician would probably say that W, which is given in the picture that you see here, is equal to the summation. And if we have infinite small particles, then we need to use the fancy way to sum. So we're going to use the integral. So the summation of all dW's. And that is a formula that will help us to understand what's going on later on when we further derive this. For now, it's just an observation. So the total weight is the summation of the tiny particles. And that then is passing through W, as you can see here in the picture. So here, W is passing through G, I should say. And let me give you an analogy here the best way I can without being in the classroom together. So I can think of a seesaw on the playground, and I can put a student here. And if I have a student with the same weight on the other side and they both have the same lever arm, then they balance out. And then they would balance about this point. So in a very abstract sense, this would be G as well, because the potato is doing exactly the same thing. So if you poke a needle into G here, then everything on the left side balances everything on the right side. And that's the same what you experience on a playground if you sit on a seesaw with somebody who has the same weight as you. So that is what the center of gravity is really about. Now let's notice another thing, and that is how G is represented here. It is given with these distances here, X bar, Y bar, and Z bar. So I need to write that down as well. I need to memorize that the distance, so distance between G and the coordinate origin is represented by X bar, Y bar, and Z bar. And one little side note, I usually would ask you this in class normally, but here I can't get your feedback. So usually I ask my students how many X tildes exist and how many X bars exist. So X tilde we discussed on the previous page. Now we're talking about X bar. So what we would come down to in the class is X tilde exist infinite times, whereas X bar exists only once. And of course that's true for the other directions too, Y and Z. So I want you to understand the difference here that we're talking about right now. So this X bar defines the distance between the origin and the center of gravity. And because the center of gravity only exists once in the potato, that also exists only once. Whereas if you look at X tilde, it was the distance between the coordinate origin and each individual particle. So that would exist infinite times as well. Last observation to be written down here is what is W now? So W is the total weight of the body. So W here is the total weight of physical body that passes through the center of gravity. And that takes us to the definition of the center of gravity. Just before I go there, let's remind us that this is a single point, right? Single point, meaning it only exists once for each potato. But now we're ready to talk about the definition of the center of gravity. So let's do that next. Let me zoom out. And let us look at this potato here. Now you see the previous two pictures combined. This is nothing new, just a little bit more convoluted because we're having both here. We have dW here There's also a dV because this is technically a small volume as well, but we're talking about weight currently. So there's the dW, which this exists many times in here. There's many x tildes, y tildes, and z tildes, but there's also the center of gravity, and that has the distance to the origin as well. And that is defined by x bar, y bar, and z bar, which only exist once. We already talked about that, or we discussed that already. So now the way the center of gravity is defined, right, is that whatever point in space you choose, let's say you choose the origin of the coordinate system, there is actually a weight times a lever arm, right? So in the x direction, it would be w times x bar. And that would create the equivalent moment as each individual particle times its distance. And again, here you see only one of them, but imagine for a moment that the entire potato is made from only 2 dWs. Then you would say that dW1 times x tilde 1 plus dW2 times x tilde 2 must be equal to the w times x bar. And that is kind of the definition, right? So I'm going to write that down here for you on the bottom for now. So x bar times w is equal to the sum of, so the sum again is infinite, x tilde dw. So, and I say that again because that's difficult to digest sometimes for a beginner. So if the potato were made from only 2 individual particles, then you had particle 1 times its distance, particle 2 times its distance would be equal to the total weight of the 2 particles times its distance to the origin. And that's really what the formula here says. And so let's write that down in words just for your definition. So the sum of the moments of all particles, the sum of the moments of all individual particles and their distance, right? Is equivalent to g times its distance, or to the total weight, multiplied by its distance to the origin in our case. But let me tell you, it actually doesn't matter to which point. This is true anywhere in space. So instead of choosing the coordinate origin here, I could also pick this point here, which, like, you know, it could be any point in space. And as long as I fulfill that let's color code it, that the sum of the moments of all individual particles and their distance, right? So that is this component here. And of course the sum is really, so let me box that. So that is the sum here. And then the individual particles is this component. So that would be the individual particle. And then last but not least, I have x tilde here. So let me code that like this. And that is equivalent to the total weight, which would be this component, and then multiplied by its own distance. So its distance, which would be that component. And so now you know that the balance is given, right? So this is nothing else than moment equilibrium that you have learned before. So in fact, let me write that down here. So this is effectively the moment equilibrium. Or in other words, it's the sum of the moments being equal to 0. That's exactly what that equation says, except it is looking a little bit convoluted or a little bit different than what we've dealt with before. And if you remember from the beginning of our lecture, where we're going with this, then you know that we are actually always be looking for x bar, right? So x bar is what the engineer will calculate, because the engineer wants to know, hey, where is that centroid actually located? And to get that, all I have to do is rearrange this formula. I have to divide the right side by w. However, before I do that, I will actually represent w here again, as we already done before. So I can also write that x tilde times the integration of all particles is equal to the integration of x tilde dw. And all I've done now is I kind of wrote my total weight as the sum of all the individual particles. And now, last but not least, what do I have to do to get my x bar? To get x bar, all I have to do is rearrange the system, and I would end up with a formula that looks like this: x tilde dw divided by the integration of dw. And this is a formula you do want to remember for sure. As I will show you in a second, it will come over and over and over again in different forms. But I spent some time here to derive this formula, because it is a formula that shows up in many different fashions from now on. And you need to understand where that's coming from. Here you understand that it's coming from weight. Later on we'll do it for volume, for mass, and for areas. But the actual formula will always stay the same. You will always see an x tilde, you will always see an x bar, you will always see an integration sign, you will always see an integration sign. What you won't see probably is a dw all the time. So this can be replaced by other things, as you will see in just a second. To be complete here, let me clarify that I can also do this for all the other directions. So for the y bar, I would just deal with the same formula, just with y tilde dw divided by dw. And for z bar, I would be interested in finding the z tilde dw divided by the integration of all dw's. And so that's the first clue that this formula, or the shape of this formula, or the form of the formula, is so important, because you see it works in all directions. And in just a second now, I will actually show you that it also applies to the center of mass and the centroid and so on. But for now, we understand that this is the formula that we need to memorize, and we understand where it's coming from. So I derived this here from the top for you. And what we need to understand to get to this point is that we have a balancing equation here, so the sum of the moments. And for now, I can just tell you that any point in space needs to balance like this equation says. We are just choosing to do it over the origin, because that will clearly define our x bar for us. And that is what we as engineers will be interested in. So that concludes the center of gravity. And now I will show you very quickly how this applies to the center of mass and the centroid. So for the center of gravity, we used pretty much the weight. And now we're going to look at the center of mass. And what you see already here is that we're not dealing with dw anymore. We're dealing with dm, which is the mass. And then we call this the center of mass here. But everything else stays the same. So the formula does not change, except that I replace my dw now. So I can replace dw with dm to obtain the formula for the center of mass. In other words, all I need to do now is rewrite my equations. So for example, if I want to find x bar through the center of mass, then I use the integration of x tilde dm divided by the integration dm. And same is true for y bar, which would be equal to the integration of y tilde dm divided by the integration of dm. And last but not least, z bar would be equal to the integration of z tilde dm divided by the integration of dm. And so once again, you only need to learn really one formula here. You just need to know how to use it and when with which components. Let's talk one last time about the picture here. So entire potato, the center of mass here has only one distance, x bar, whereas the individual small element, the small mass element, exists many times and therefore has many x tildes. Let us, before we move on, conclude, or I guess reiterate, that the center of gravity and the center of mass are both physical properties. So these depend on what the potato is made from, right? So it's very important to classify this for now, that it's a physical property. And it depends on what the potato is consistent of. So if you have a potato that is more dense, it has a different behavior than a potato that is a little bit less dense. Or even worse, if you have a potato that has different densities throughout, then you have to be very careful with this. Don't get me wrong, in this class we are not dealing with those different densities, but to understand that the center of gravity and the center of mass are physical, it's important to understand that those are properties that depend on the material that makes up the potato. This is very different for the next thing we're going to talk about. So now we're going to talk about the centroid, and you will see that the centroid, first we will of course talk about 3D objects because that's where we're coming from, but the centroid is actually a geometric property. So now let's start and analyze that. So the centroid is a geometric property. So that means independent of what the potato is made from, only the volume matters. So that means, as you can see here in the picture, I actually don't have a mass element anymore, but instead I have a volume element. And that is the only difference here. So very similarly, I can deal with 3D objects. This is a 3D object here, and this is as high as we go geometrically here. Of course, you can also do it in 2D and 1D, which we will do down the road. But we are purely dealing with geometry here. So we can say that similar to before, the coordinates of the centroid of a volume can be obtained by replacing or rearranging parts in the formula. So similar to before, similarly, the coordinates of the centroid which is a geometric property, can be calculated by replacing W or M by V for volume, or also A for area, or L for length. And so it is not a difficult formula, or once again, it's the very same formula. So we can now write down the formula for the centroid location, which is the one we really will need a lot in this class. And that is x bar is equal to the integration of x tilde d volume divided by the integration of all the volumes, which is just the total volume. Similarly, for y bar, I can take the summation of y tilde dv divided by total volume. And last but not least, z bar is equal to z tilde dv divided by dv. And so now I can clearly differentiate between the two physical properties, which are the center of gravity and the center of mass. We derived the center of gravity in very long lengths, and we then quickly moved it to the center of mass because it was just a rearranging of the formula. And then we moved to a geometric property, which is only dependent on the actual shape of the potato and has nothing to do with what it's made from. And so for us here in this class, that's mostly what we'll be dealing with. In fact, we will actually take it one further down. We will go down from d volume to d area, but the derivation is the same one. And you also might have to deal with it in 3D here and there. So that's completely derived now, again, for physical properties and for geometric properties. And hopefully the difference between the two is clear now. So now we can move on and reduce it further down to area objects. So what I want to talk to you about next is the centroid location for an area. And remember our formula from before when we talked about the volume. It was x bar is equal to the summation of x tilde dv divided by the summation dv. I now take this down to an area, or like I'm going to talk about areas only now, and therefore I'm going to call it the summation of x tilde dA divided by the summation dA. And once again, this here just stands for total area. And also, this part here on the top is called the first area moment. So you sometimes read in textbooks first area moment. Why is it an area moment? Because you have an area times the lever arm, and something times the lever arm is considered a moment. And later on we'll talk about second area moments, but for now this is the first area moment because x is linear in this case. And I want to now show you how to really bring this down to more like a numerical sense. We're not solving the problem yet, but I want to show you with these pictures down here how we can really make this equation a reality and how can we integrate over dA. So let's go to those pictures, and for now I just want to focus on these two and let's analyze them first. So I have an area that has a right angle down here at the origin of the coordinate system, and there's just a random shape here, right? And that random shape is defined by the function y, which also is a function of x in this case. Of course, it could be a function of y as well, but here in this particular case, let's just pretend it's a function of x. So that means for every x value, I get a corresponding y value. You know this from other classes, of course. This area has a centroid location, so that is pretty much where all area elements balance, just like we talked about before. And that has a distance to the origin. So that distance is defined as x bar and y bar. And that is exactly what we wrote down here, right? So x bar is equal to something. And now we want to talk and look into this equation a little bit more. So what is dA, right? So that is a component that we have. So actually, in fact, we have two components. So I'm going to put my equation up here. X bar is equal to summation x tilde dA divided by summation dA. So I need to know two things. I need to know what is dA and what is x tilde. So again, we're dealing with this form here. And so now I'm going to move to the right side and I want to focus on the drawing here. So the area element here is given, right? So this is considered dA, the blue shaded area here. And again, for every x value, so if this is my x value down here, then I get a height for that value, right? So I can now define this height by the function f of x. And so my dA really is base times height. And the base happens to be dx and the height happens to be the function. So I can write that down as well. So my dA is really equal to y times dx. And this is the base. And this is the height. And of course, this is also equivalent to f of x times dx. And now I'm pretty much almost done. I need my second component, and that is defined down here. So for every dA that I analyze it at x. And that means that for this dA, the distance to my origin must be x tilde, and that is x, right? And so that goes here. So I already understand that my x tilde is equal to x for this particular case, right? Or for this generalized case integration over the x-axis, right? So notice that I am integrating over the x-axis because I'm using dx, right? And so now I am effectively done here. I have deciphered what goes where. Let's do that for the third picture on the right side, because this is now actually an integration over the y-axis. So here I have the area element that is horizontal, and that will be a little bit difficult, like if I have a function given in terms of x. However, if I have a function given in terms of y, then that will make this easier. However, conceptually speaking here, I have dy as the base, and then the height would be x, right? So in this case, my area element, so here dA would be equal to x times dy, right? And notice that here my x tilde is given with x over 2. And let me explain that a little bit more in more detail. So here you see that this is the centroid location, right? So remember that the x tilde is actually the distance from the origin of the coordinate system to the individual particle, but the particle actually does have a centroid as well, although it's infinitely small. And here, since you're now integrating over the entire height, you actually need to take, or the entire width of this area, you need to take half the width. So this would be the distance from the origin of the coordinate system to the centroid of that individual area element. And that's how you can deal with these problems. Of course, if you deal with y tilde in this case, right? So y tilde here would be equal to y. And that is also shown in the picture. So here the distance from the origin in the vertical direction to the centroid of that location of the centroid for the individual area element, that is given with y in this case. And so in sum, all we have to do is rewrite these equations that we had before for x bar, which I already did that, but I'm going to repeat it down here anyways. So sum x tilde dA divided by sum dA. And then for y bar, it is sum y tilde dA divided by summation dA. I repeat it one last time. Total area, first area moment about the y-axis actually, and first area moment about the x-axis actually. So let's write that down because you see that in books sometimes. So this component here is the first area moment about y-axis. And now you ask why? And I explain that to you. So if you think of this area element and you use x tilde, then you're using this distance, right? And so think of it as this area element rotating about this axis, right? So that is the case for that. And then here we, on the other side, we have the first area moment about the x-axis. So first about the x-axis. It's a little bit counterintuitive because you see a y in that equation, but that's exactly how that comes across. So let's take a look at this part here now. So if I take this area element and rotate it about the x-axis, then I have to use y tilde as a lever arm. So that's why it is the first area moment about the x-axis. And I think that concludes that component. So we now brought down the actual formula for the centroid location to a centroid location of an area. And here we're doing dA, but ultimately we're actually taking it down to dx. And I will now down here give you more instruction on how to do that, but please note that we're actually not integrating over dA. I mean, ultimately we're doing that, but we are really numerically integrating over dx. So we bring it down to one variable along one axis, either dx or, if you look at this case here, dy. So, and this side here would be more beneficial if you have a function that's not f of x, that's actually like a function of y. And if you use this picture here, then it's better to integrate over dx when you have a function that is f of x. So this is more appropriate for f of x. This is more appropriate for f of y. So I'm going to zoom that in so that you can take those two pictures and take a second look at it. But then I will move on and write down the actual steps to how to calculate these things, and then we will apply it. So let's move on. So you see we really have 4 steps to do that. So here comes the instructions for finding the centroid location of an area. And first what I have to do is I have to choose an appropriate differential element dA. So first choose an appropriate differential area element dA at a general point. What does that mean? That means what I've done here in blue. I point to it for you. So I choose this, for example. Or if I had my function of y, I would have chosen this. But I'm going to stick with the middle picture now for the instruction here. So I choose this here and I drew this in here. And then in my next step, I use that dA and express it properly, right? So now I'm going to express dA in terms of a differential length. And usually our initial goal would be to do it in terms of dx, but sometimes you also might to do it in terms of dy. So let me zoom in to show you what I did there, or what the second step. I mean, the second step is technically connected to the first step, because once I choose dA, I kind of also define if I want to integrate over dx or over dy. Again, for now I stick with dx. Once I've done that, I need to pretty much define the centroid location. So define the centroid coordinates, or determine. Or the coordinates for x tilde y tilde. And that is of the rectangular, which has a base times height, element. And you do that at a general point. So at a general point. Let's look at that. So if I look at that here, I pretty much decided, hey, I have my dA here in my first and second step. I decided that I have the base and the height defined for my dA. And now I need to find this point. That is step 3. So I decided that this is the location of my centroid for this rectangular area. And so therefore I know exactly how to define x tilde, and I know exactly how to find y tilde, or define y tilde. So that's the third step, how to define those locations. And then last but not least, I just have to express all variables and integration limits. So express and integration limits. In terms of x in our case. But you also might do it in terms of y. I'm not doing that here. Depending on the differential element, and then you integrate. And then integrate. You can also call that solving it, right? So you solve equation. Let me go back to my picture up here to explain that. So what would I have to express? I would have to express my integration limits here, for example, from 0 to whatever this value here would be. And then I integrate my function from a to b, and then I have solved it. And that concludes the definition or the derivation for the area centroid. And in the next step, we will now take these 4 points and solve a problem accordingly. But this is the derivation of the centroid location of an area. So now I'm ready to solve my first problem here. Very basic problem, as you can see. We have a function that is just x cubed. It's very simple. It almost doesn't get any simpler. But we have a width of 1 meter and a height of 1 meter. And the question is, what is the centroid location? Actually, this should be x bar and y bar for that area element. So let me fix that. So x bar and y bar. And you pretty much should do that through the integration steps that we just done. So now let's work our way through it. Remember step 1. The step 1 was to show a differential element. So I will do that for you. So I will just draw a random element in here. this is my random element. And I'm going to call this here dA. And really, I'm integrating over dx. So I have my width, which is dx, and my height of that area element is really f of x, which actually is equal to x to the 3. And so remember that our formula was x bar is equal to integration of x tilde dA divided by integration dA. So now what do I have to do? I have to integrate or fulfill those criteria here. And I already found that dA, where do I write it here? dA is equal to x cubed dx. And again, this is the height. And this is the base. Base times height. Now, what is my x tilde for that particular area element? Remember that now I expressed dA in terms of dx. So this was my step number 2. My step number 2 is pretty much done here. My step number 3 was determine the centroid location. So I have to define, hey, where's the centroid location of this? And it's a rectangular element. So it's exactly in the middle here. And what that means is that I have a x tilde for this element and for any other element that is equal to x, right? So even if I move my area element, this area element here, if I move this further to the left, then I would still integrate at x. And so this is true for no matter where my area element is. And therefore I can now say that my equation up here is actually equal to x multiplied by x to the 3 times dx. And of course, the whole thing integrated. And last but not least, I need to integrate the entire area, or I need to find the entire area, and that's just x3 dx. And all that's left to do for me now is use integration constants. So I'm going to write that down here on the bottom again. So my x bar is equal to x to the 4 dx, and this whole thing integrated, divided over x3 dx. So just to be clear here, I have power 4 because I have the double x here, and then x to the 3 comes from that. And now I need my integration constants. So I need to do this from 0 to 1 and from 0 to 1. And now all I have to do is integrate this properly. So I'm gonna, if I integrate this, I get 1/5 x to the 5. And I do that from 0 to 1, divided by 1 over 4 x to the 4 from 0 to 1. And when I solve this, I pretty much end up with 1/5. This is a very simple example, divided by 1/4. And that ultimately ends up being 0.8 meters. And the solving here is really not the problem, right? So let me point to it. So everything here is not the problem. Everybody in the class can usually do that part. The question is, how do you derive this equation? And we spent quite some time in this lecture to really get there, starting from the center of gravity all the way down to area elements. And now here I'm actually implementing this. And I hope those 4 steps are clear to you, thanks to what I wrote down up here. But this is really the challenge, how to set up the right equation. Solving this, everybody can usually do. Last but not least, I, of course, even though it's simple to solve it, I should check my result here, right? So, I mean, I'm 100% convinced that this is correct here. But I can also convince myself that for an area that has a length from here to here of 1 meter, that an 0.8 is a good value, right? Because if this was a triangle, by the way, and I'm gonna put that in here just for fun, and so you know how I think of these problems. So if I had a triangle, then I would exactly know how large my x bar would have been. It would have been exactly 0.66, right? Or like 2/3, if you will. And now in this case, I'm actually carving out a component. That means the material gets heavier on the right side relative to where it was when it was a triangle. And therefore it needs to be larger than 0.66, which is the case. Also, it cannot be larger than 1, and that is also the case. So I solved this. So that's fairly straightforward. So I solved for x bar. Now it's time to solve y bar. I encourage you to do this and pause the video for a second, but I will move on and solve it for you. So what is y bar again? Y bar is equal to y tilde dA divided by dA. And so now the only thing that's different is my y tilde. So let's analyze that real quick, and it's probably best to look at this picture here. What is y tilde? Y tilde is the distance between the centroid location and the origin of the coordinate system. So that would be this distance here, and that would be y tilde, which is equal to 1/2 f of x, which is x to the 3, right? So that is my distance here. And now the rest I can do as before. So I have 1/2 x to the 3 times dA. So, which remember was nothing else than x to the 3 dx. And my area does not change, right? That's also important to understand, is that the area, of course, cannot change, so it still remains x3 dx. So if I integrate that now, I end up with 1/2 times 1/7. So 1/2 times 1/7 x to the 7. And I integrate that from 0 to 1 as well. And then here nothing changes. In fact, it's 1/4 x to the 4 from 0 to 1. And if I solve this now, I end up with 1/14 divided by 1/4. And ultimately with 0.2857 meters. And so now I need to double check that result as well in my sketch. And in fact, the very last step that I have to do is really look at my sketch, but it was like less than 0.3. And that makes sense as well, right? Because the heavy side of this, what used to be a triangle, is here on the bottom. And so if I carve this part out, it slides more down. And so for a triangle, it would be 1/3, which would be 0.33. But the carving makes it drop further down, and therefore I'm done. Although the last thing that I really have to do is show in my sketch that I understand where it is. So let's say I pretend it's right there. I need to clearly identify that the distance here would be equal to 0.8. X bar is equal to 0.8 meters. And then last but not least, the distance down here would be y bar, which we calculated to be 0.2857 meters. And that is the final answer to the problem. And I believe that is a simple problem to follow. I'm not saying it's simple so that you need to immediately understand it, but it should be understandable once you study it and maybe you play the video a few times. Maybe you got it already. However, this is, I think, a good introductory example that helps you to understand all the components and follow the 4 steps. I'm going to repeat the 4 steps here real quick. So first thing is to find a random element, which I've done here, and then express dA in terms of base times height, which I have done right here. And then you pretty much determine the centroid location, which is this part here. And you define x tilde and y tilde. And then last but not least, you solve your equations using your integration constants. And that concludes this problem. And I will move on to the next one. So in this problem, it becomes a little bit more interesting because we're really dealing with like a structure, if you will. And so let's read the problem statement. There's a structural plate that is made from concrete, which is 2.5 times as dense as water. And it has a thickness of 5/15 meter. That's of course a strange measurement, but that will make our numbers easy. And now you are supposed to determine the support reactions. So just as I explained to you in the beginning of the lecture, when we talked about the homework, what's going on here now? We have a plate that has a centroid, or centroid location. So I'm going to call that C. And there is a force that is going through there. I'm going to call that F plate. And that plate has a distance x bar. And that is what I need to calculate my support reactions, because my support reactions are twofold. I have these guys. I'm going to call this RAY, RAX, and then also I have RBX. And the easiest one to find is RBX. So by taking the sum of the moments about point A, sum of the moments about point A is equal to 0, counterclockwise positive, and 0 is equal to RBX multiplied by the height, which is 2 meters. And then that turns counterclockwise, so I'm going to make that positive. And now I have the F plate multiplied by x bar, and that turns clockwise, so therefore that is negative. And I will be able to solve that equation in just a second for RBX. But before I do that, what I need to do is I need to find how heavy is my plate and what is my x tilde. So let's start with the x tilde because we have done that before, or that's what the lecture is really about. So I need to follow my 4 steps again. I choose a random area element, and I'm going to draw that right here. So I have a random area element. I'm going to call that dA. And dA is really nothing else than base times height. So dx times f of x, which then ultimately turns into, and notice there's a negative, minus 1 over 4 x to the 3 plus 2 times dx. That is my area element. Now I need to identify what is my x tilde. Notice that I don't even worry about the y bar or y tilde. I only need to care about the y tilde. So let me put that in here. So the centroid location of this system would be right here. But I only care about the y direction, sorry, the x direction. So I'm going to care about this component, which is x tilde, which is equal to x once again. So fairly simple in this case. And so I know that my x tilde is equal to x. And now if I write my standard equation for x bar, right? X bar is equal to the summation of x tilde dA divided of all dAs. Now all I have to do is grab my components from here and here. So my x tilde is x. So I'm going to use the red color for that. Or actually, let's change colors here for a second, so it's easier to follow. So x and then times 1/4 x cubed plus 2 dx, and my entire area is just -1/4 x to the cubed plus 2 dx, and of course also integrated. And now it's a question of solving. I need to think about my integration constants. So let me first rearrange everything here. So I have -1/4 x to the 4 plus 2x and all of that dx. And I divide that by still the same thing. But I'm going to do that from 0 to 2. 0 to 2, because I'm integrating over x for that plate here. And if I now rearrange everything, then what do I end up with? I end up with something that is -1/4 times 1/5 x to the 5 plus 2 times 1/2 x to the square, and the whole thing integrated from 0 to 2, and I divide it by the entire area, which happens to be -1/4. Don't forget the negative, that's important, although obviously you cannot have a negative area, but the function here is negative, so that needs to be included. X to the 4 plus 2x, and that also needs to be integrated from 0 to 2. And if I do so, and again, that's not the part here of the class, right? But ultimately you end up with 12/5 divided by 3. And that ultimately ends up to be x bar being 0.8 meters. And that is technically a result, or at least a result within this class, like within the purpose of what this class is about. And so now I solved for my x bar. However, it's not the full result, because remember, now I know that I can fulfill this equation here. And what I know is that this here is 0.8 meters. So the question remains, how do I find F plate? Like, how do I get this one? And the answer is straightforward. It's made from concrete, and I know its thickness, right? So I know its thickness being 2/15 meters, and I know that it's denser than water by 2.5 times. So all I need to do is calculate the area, and then multiply that by the thickness, which gives me the volume. And once I have the volume, then I can multiply it by the density to find its total weight. So let's do that next. So I'm going to do that down here. So F plate is equal to the thickness in meters, by the way, times the area in meters squared, so which is a volume then, multiplied by the density, which usually is called rho. And that is usually in kilograms per cubic meter, but I'm gonna just violate that a little bit and go in kilonewton per cubic meter, because that's what we're ultimate after, like as a force, right? So let's look at that the thickness was 2/15 meters. The area I already calculated, right? So this here is actually the area. So multiplied by 3 meters squared. And then the density of water is 10, or not really the density, the specific weight, 10 kilonewton per cubic meter, and then multiplied by 2.5, because that is the density of concrete. And if I solve this, I will find that my entire plate has a nice weight of 10 kilonewton. And now I can substitute that here. That is equal to 10 kilonewton. And now all I have to do is rearrange this formula, and I'm just going to do that up here because I've written it anyways. So I can say that RBX is equal to 10 kilonewton multiplied by 0.8 meters divided by 2 meters. And when I solve that, I find that my RBX actually happens to be equal to 4 kilonewton. And that is an ultimate result here for this. And of course, solving that is not the problem. But I can include that here now in my picture. So I know that this must be 4 kilonewton. And by the way, notice that for me it came out positive because I assumed already RBX to go to the left side, right? I want to re-emphasize this here. And I also know now for the sum, because of the sum of the forces in the x direction being equal to 0, I also know that RAX is equal to 4. So I know that this is equal to 4, right? And my RAY must be equal to F plate, which therefore is equal to 10 kilonewton. And now I solved exactly what the problem was asking me to do. I found all my support reactions, right? So determine all support reactions for the system. And I have done that based on the shape of the plate and based on its materials. So here's everything in an overview, which I believe should be you should be able to follow it. If not, pause your way through the video and play the parts again that were difficult to understand. And of course, if you have questions, you know how to reach me. But this concludes the real example, something you probably would see in the real world or actually in the exam that you will have for problems like this. So I can now move on to my last part of the lecture. Let's do it together. Of course, first, you only know what your takeaways were, and please clarify those for you. Also, please ask yourself what didn't you understand and which parts still need clarification. But ultimately, what you need to take away from this is that everybody consists of an infinite number of extremely small particles or infinitely small particles. We understand that, right? They also have a super small weight and they have a certain distance from the origin. That is important. You understand that. So that is what we called actually x tilde, right? That is that part. Here we call it, for example, dW or dm or dV or even dA. All that was the same. Now, you understand next that the center of gravity is the point at which all the resultant weight is balanced, or even the mass and so on. So this is the balancing point, and that is the point of checkbox number 3. And now you also understand the difference between the centroid and the center of gravity, because the centroid is actually a geometric center. So this has nothing to do with the material or anything. And because it's geometric, you can do it for a volume, for an area, or for a line element. We, of course, didn't discuss line elements, but I think everybody would be able to conclude that themselves. Last but not least, you can now mathematically solve these problems. And of course, the ultimate goal is to find the support reactions using these random shapes. So now you can solve this. And that concludes the lecture. Let's take a final look at the homework. So here you have random shapes, centroids, given in terms of function. Notice that each shape here is given with a specific function. And that you now need to find only the centroid here and here, but here for these two problems you are supposed to find the support reactions. Now this problem here is slightly different from what we had as an example, because remember that when you integrate, and actually this is true here as well, so here you get to practice that. Remember that when you integrate, you always find the area under the curve, right? So here you find the area under the curve. So you have to find a trick for these two problems to integrate for such that you find the area above the curve. So if I look at that conversely down here and here, if you integrate from 0 to 3 here, you will immediately get the correct result because you integrate the shaded area. But if you, and the same is true here, by the way, of course, it's a strange integration constants, but that's because of the function. Sorry, not integration constant, but integration limits. So 0 to 2.183. But if you integrate this, you will immediately find the answer for the area, whereas for this problem and this problem, you actually, if you were blindly integrating, you will find the area under the curve, and that's not what you want in this case. And in this case, you want the area above the curve. So please pay attention to that. And that, I think, is everything I can tell you about the homework for this topic, and I wish you good luck with that, and I'll see you in the next lecture.